So continuing, let's look at how to determine the oxidation states of complexes. So I'll start with easier ones. For example, if I had, which example can I use here? I can use carbon dioxide. So I'm just assuming that I didn't know the oxidation state of carbon dioxide in this particular compound, which is carbon dioxide. So to get the oxidation state of carbon, what do? I need to do about two things or three. The first one is you must know the type of ligand. What do I mean? So whenever we're looking at this, we shall find that we have neutral ligands. So this is what I mean by type. It can be a neutral ligand, that's if it carries no charge, or it can be a monoionic, get monoionic or an ionic, monoionic. So I'm calling it monoionic, or it can also be called an ion that is negatively charged or positively charged, you get? Then we can also have diionic ligands. So what I mean by diionic is that it has a double charge. An example of neutral ligand, we are going to look at the examples. For example, can have ammonia. We can have another neutral ligand. We have water. We can have as many as possible. So your assignment will be to find the common neutral ligands we have and the inorganic. Then the monoionic, we can have the halogens. For example, the fluoride ion, can have the chloride ion, we can have the bromide, the iodide, we can have the hydroxide or the hydroxyl ions, we can have the cyanide, get the cyanide, we can have as many monoionic ligands as possible as well. Then the dianic, we can take an example of oxygen, which is dinegatively charged. We can have the oxalate. This one we've seen it under organic chemistry. Oxalate, for example, we shall see it commonly. So these are some of the ionic. And then you also need to find the various neutral ligands. They can be very many: nitrogen monoxide, carbon monoxide, you get? So all those are neutral ligands, you get? So you must be knowing whether it's neutral, monoionic, or diionic, but you find that the examples we use are actually almost the same. So that's the first thing I must be knowing whenever I'm going to find oxidation state. I must know the nature of the ligand, you get? Then the other thing is to look at the number of ligands, you get? For example, I'll take an example of this. Oh, let's go back to our carbon dioxide. Our central atom here will be carbon. Then the number of ligands, which are the oxygen atoms, will be how many? 2, you get? So here I determine the number of ligands, which are 2, you get? So that's the second thing to look at, the number of ligands. But however, they can also be different ligands in the same complex. An example is this: have water, you have chloride. And then after knowing the number of ligands, look at the overall charge of the complex. For example, what's the overall charge here? It's a plus 3. You get? What's the overall charge in carbon dioxide? It's 0 because it has no charge. Then if we look at this one, what is the overall charge? So this one, it's a bit tricky in that the charge is actually hidden in this potassium. What do I mean? Is that if I know my potassium ions are actually positively charged and I have 4 of them bonded to this complex, yeah? It means that these ones must also be what? Must also be 4 and of the opposite charge, which means that I have iron, then the cyanide 6, this whole thing into brackets minus 4 negative. You get? So in other words, if we look at the formation or the balancing of equations, we see how these valences move and come about to form that. So this means that I have 4 potassium ions and this complex with a 4 minus charge. You get? Or in simpler terms, I would just say that how did I form this complex? This complex I needed 4 potassium ions, which means that this one had a charge of negative 4. You get the point? So this one had a charge of negative 4 or 4 minus. That's why I needed 4 positive ions. That's how I will know the charge on the complex. The same thing applies here. When we look at this, they have given us a 2 plus as the overall charge of this complex. Then they have put the 2 chloride ions. In other words, someone would have left out these charges, would have removed this, would have removed that, and that negative. It would still mean the same thing. So you need to be very keen when you're looking at the overall charge. So whenever we're looking at this complex, we are not considering these atoms that are actually outside the bracket. What we are looking at is actually the central atom, which is the transition element in this case. For example, iron here, we have chromium, also chromium here. But we are leaving out the atoms outside, which are just helping us to know the charge of the complex. So with that basic explanation, we can start. So how are we going to do this? After knowing whether it's a neutral or what, then I also know the number of ligands. I know the overall charge of the complex. I know the overall charge. Then what am I going to do? What I'm going to do is that I need to find the oxidation state of the central atom, which is the transition element in this case. For example, here it's chromium. So what I don't know, I'll assume that or I will let its oxidation state be any unknown. For example, I can write that let the oxidation state of chromium in this complex be M. You get? So I'll assume that or let it be M. After letting this unknown to be M, what am I going to do next? What you're going to do next is that it will depend on your understanding that the sum of the oxidation states of all these atoms or molecules involved in the formation of complex, it will be equal to the overall oxidation state. You get? So the oxidation state of chromium plus the oxidation state of the ammonia will be equal to the overall oxidation state. So I have chromium, which is M, plus What is the oxidation state of ammonia? It's a neutral ligand, so it will be 0. However, there are 6 ammonia molecules, so I'll multiply the oxidation state by 6 and then equate to the overall charge. Overall charge is written as either plus or negative. It's not a superscript or subscript, it's always in the middle here. It may not be as big as I've drawn it. So something like that. It must be in the middle. Don't write as superscript, that is up, or subscript. It should be in the middle. That's how we write our values. Especially, this may not be so much of, there may not be emphasis on this point, but whenever I'm writing the oxidation state, always remember that it's written with a positive or minus, that's the charge, in the middle, then the number. Get? So what will be the value of M here? The value of M will actually be positive 3. And that's how I get my oxidation state. So the oxidation state of chromium in this case will be positive 3. Don't forget the sign, positive 3. And always don't just put their unknowns. Show the examiner that I've let the oxidation state of chromium be M, so that whenever he sees M, he knows that you're talking about oxidation state of chromium or that particular element. So we can also try out the next one. The next one is in this complex. So I've said that actually what we have here is this complex. We have our iron, then the cyanide. So what was the original charge on it? Take back the 4, it will be minus because it was neutralized by 4 positive ions from the potassium. You get? So this is the actual complex in this. So the overall charge will be a negative 4. So even here, I'll let the unknown oxidation state of iron be, let's say, P. I can let it be P. So I'll say P, the oxidation state of iron, plus, what's the oxidation state of cyanide? It's a negative 1. It's a monoionic. So I'll have negative 1 multiplied by the number of the cyanides there, 6. And that will be equal to the overall charge, that's a negative 4. So my P will be equal to, if you take the negative 6 that side, it becomes a plus. So I'll have negative 4 plus 6 to give me a positive 2. And then you can come and conclude that the oxidation state of iron in this complex is a plus 2. Trying out one more, let's look at this one. So this one, we can see that the overall charge is a plus 2. And I'll let the oxidation state of chromium be, let's say, M. So M plus, what's the oxidation state of water? It's a neutral ligand, so it's a 0 multiplied by the number of water molecules, which are 5. Then plus, I also have a chlorine or chloride. So what's the oxidation state of chlorine or chloride? It's a negative 1. It's a negative 1. How many? It's only 1, so I can multiply by 1. And that will be equal to the overall charge, which is plus 2. So once again, I've said that don't consider these atoms that are outside. They're just helping you determine the overall charge. So our M in this case will be equal to half 0 plus negative 1. If you take out the negative 1 to the right, that becomes a plus. So you have 2 plus 1 to get a 3. So that's how you get the oxidation states. I've written one more here. You can also try it out. And here you'll find that the oxidation state of copper is actually, you have here, you can let it be X. So X plus how many chloride ions? are 4. So 4 multiplied by the oxidation state, which is -1, plus 4, that will be equal to the overall charge, which is -1. So my x will actually be equal to a 3, if you see it well, a positive 3. So always be careful when you're writing this sign. It should be in the middle, just it's something small, not too big, like as if you're writing a T. Write a plus. Mine may not be perfect here because I'm not using a pen to write. I'm just using my simple pen. I mean mouse. That's why it may not look too good. But when you're writing, make sure that you write a small plus in the middle, then the number, like that. So that's it about oxidation states. You can get as many questions as possible. You can actually inbox. I can send you more questions for practice about these oxidation states. So after understanding the concept of oxidation states, we can go on to get or to look at the nomenclature. Now, how shall we name this? How shall we name that, and so many others?